Okay. Let's recap. What did I do last stream? Ah, that's too far. Too far. Helmholtz. How far do I need to go back? Circulation. Circulation. Um, Circulation of a vector field on a closed group C is defined by like basically dot product. Yeah. Circulation along a closed curve. Part C. So the direction matters. Um, ah, helical pipe. For like a pipe, the circulation you can get from this. Um, Consider blah blah blah. Um, hmm, curl the right side. Blah blah blah. Curl. Um, the curl of a vector field VR at a point. The curl of a vector field at a point R in space has the interpretation that its component along the n direction, is given by the circulation per unit enclosed area V around a really small loop surrounding R on a plane perpendicular to N. Um, this is complicated, but I know what it means. Uh, this circulation is going to be this circulation is to be calculated along the positive right-handed direction relative to N. Stokes' theorem, you can represent the circulation as um, integral over a surface. It says that the circulation around the closed part is equal to the flow of the curl across the enclosed area. Flow of the curl across the enclosed area. Circulation is caused by flow of curl. Um, okay, show the gradient, blah blah blah. The conservative force, which is derivable from potential, is irrotational. Converse is also true. Um, in fluid dynamics, the curl of a velocity field, which gives the velocity of the fluid at point R. The curl of the velocity field is called velocity. Um, if the velocity depends on a scalar field, it is derivable from a scalar field. It must be irrotational. And irrotational flow is also called potential flows because it comes from a potential. Um, Being thus free of vortices and eddies, it describes a steady flow. So a flow that is derived from a potential field is results in a steady flow. Like there's no like curving. I assume from these sentences. Maxwell equation has something like this. This states that the circulation of the magnetic induction is proportional to the total charge passing through the surface. Closed by C. Um, it doesn't matter if it's a plane because if it's a curved surface, as long as you go smaller and smaller, it'll turn into a plane, and then you just add up all the planes to get the total surface stuff. Hmm. Calculate this for the vector field. Blah blah. Operator identity. Stokes theorem. Hmm. Hmm. this Stokes theorem to operate identity. This, if anyone is here and listening to me, I'm just really skimming through what I did last stream. Ah, if VR is this result generalizes Stokes theorem to the operate identity. Bling, bling. If Stokes theorem for this vector field reads, um, hmm, if this and this are both independent of Z, you get Green's theorem in the plane. Okay, let's go to Helmholtz's theorem. It's not accidental that the divergence and curl of a vector field play such important roles. The significance is made clear by Helmholtz's theorem, which we now stated without proof. Okay, maybe they'll prove it later. A vector field is uniquely determined by its divergence and curl in a region of space, and its normal component over the boundary of the region. So we have a region. A vector field is uniquely determined by its divergence and curl in a region of space, and its normal component over the boundary of the region. I'm not sure why this is the case. Why not the normal? Why not the normal like inside as well? Why only the boundary? Maybe it's a thing where um like how you have some loops where it's like one is going in one direction and the other is going in another direction. They cancel out, so only the outsides matter. Maybe it's something like that. In particular, if both divergence and curl are specified everywhere, and if they both disappear at infinity, what does that mean? If they both disappear at infinity fast enough, then the vector field can be written as a unique sum of an irrotational and a solenoidal part. A vector field is uniquely determined by blah and blah. In particular, if both of this is specified everywhere, and if they both disappear at infinity, what does that mean? The vector field can be written. In other words, you can rewrite a vector field as uh, curl divergence. This is the curl. Is this the divergence? Isn't divergence the dot product of the gradient vector and whatever? Where this is the irrotational part, and this is the solenoidal part. This can be seen with the help of 1.5, which show that the curl of the gradient of a scalar function and the divergence of a curl of a vector field vanish identically. The fields phi and a. Oh look, there's two fields. It's not simple. A vector field is uniquely determined by its divergence and curl in a region of space. Vector field, divergence and curl. The fields this and this are called the scalar and vector potential, respectively, of this. So If you're rewriting this as the divergence and curl, you'll end up with two different fields, Each of them are called scalar and vector potential. The Helmholtz theorem will be derived in a later chapter using, so that's why they say just assume it's true for now, because it's very complicated. Using the method of 3D Fourier, I have no idea what this means, transform. It turns out to be related to decomposition of a 3D vector into components. Decomposition of a 3D vector, so a vector with three components, into parallel and perpendicular to a certain direction, ek, in a certain shenanigans, as we did like in an earlier example. It turns out to be related to, so instead of writing this guy in three components, you can write it in two components maybe, a parallel and perpendicular, into parallel and perpendicular to a certain direction. So you have a direction and the parallelness and perpendicularness. If you combine these, you'll get this vector. It turns out to be related. It is useful to express the divergence and curl of VR in terms of the scalar and vector potentials. From this, we obtain these results. One result and this like double result here, where the last step is made without the help of the operator. With the help, not without the help. With the help of the PSC rule. It turns out that blah vanishes. This thing vanishes under certain conditions. Example, when the curl is either bounded in space or vanishes more rapidly than 1 over r or large R. So it's another thing where this becomes negligible really quickly. Or like just not relevant at all for some reason. The gradient of the divergence. Bounded in space. Is there a connection there? The curl bounded in space makes this thing insignificant. Okay, they're just gonna keep on yapping, so let me pause for a bit to hone in on what they were saying here. This can be seen with the help of equations 1.5 or 1.51. So let's go get 1.5 and 1.51. Let me check if anyone is here. No one is here. At least no one is chatting. Okay. 1.5, 1.51. 1.5, 1.5. This is really early. 1.5. Oh my god. I don't want to scroll too much because copyright. 1.5. Okay, 1.5 is this. 1.51 is this. So let me copy paste to like a separate, like to right here, I mean. Copy, my friend, copy. Copy, you, paste, you. You transform, get over here, get big, maybe not that big, like maybe I just need to zoom in. Let me get my next friend, 1.5. Hmm, J. Wait, I didn't deselect. Uh, oh my God. Transform, you, come here, make you a little bigger. Um, transform, can I move you? No, I need to switch layers. Layers, window, layers, layer 5, complicated stuff. Select you, transform, move you over here, make slightly bigger. Uh, transform, uh, deselect, you get out, zoom in. Voila. Now we can get back to business. Okay. In other words, we may write this, where this is the irrotational part, arrow, and this is the solenoidal part. Is that you need to make division and curl? Okay. This can be seen with the help of this, which show that both bling and bling vanish identically. The vector field is included to by divergence and curl in a region. What are we looking at? What are we looking at? Divergence and curl. Okay, let's start over here. The divergence of V equals this, apparently. Divergence is, let's do the x term first. Del L x, Vx. Um, where did we get a second del from? Del dot V. Is there a secret del in here somewhere? What? It is useful to express the divergence and curl in terms of the scale and vector potentials. Vector potential. Where did we get a second del? Del x Vx plus del y. Oh, I see, I see, I see. Um, this this is a vector field, and this is a scalar field. So from here to here, there was some. Hmm, hmm. Like maybe if you suck out the vectorness out of this, you end up with a scalar, and then you combine them to get um the Laplace. Is that even how you pronounce it? That's how I read it, Laplacian, Laplace. Negatives. Well, let's go to this one. Divert the curl of V. The curl of V is I, J, K, del L X, del Y, del Z. Then we have Vx, Vy, Vz. Okay. Oh my God. Curl of V equal this. Um. Oh my God. Del. Hmm. Del. Do I need to really use the epsilons here? Is that what's going on here? I don't really want to. Hmm. Gradient of this. Where the last step is made with the help of the operator form of the BAC rule. Well, either way, all of this is going to be explained with like we're doing all this, like we're doing all of this justification just to be told, we will accept this without proof. So maybe I should just accept all this, quote unquote, without proof. But at the same time, I feel like I can do this. Like if I felt like it, I can do this from this stuff in chapter one with like epsilons and stuff. Um, no, not epsilons. Well, yeah, epsilons, same thing. Levis civitas. Let's just continue. Hmm. In other words, we may write this, where this is the rotational part, this is the solenoidal part, would show that bling bling and bling bling vanish identically. Dot V equal this. Like maybe this is the result of, like maybe there's supposed to be more terms, but since these vanish, they just don't include them here. Like maybe that's the case, uh, as well. The fields this and this are called the scalar and vector potential, respectively of VR. The Helmholtz zero, blah 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 blah. It turns out you can 3D vector could be rewritten as a parallel perpendicular to a certain direction. Blah blah blah. It's useful to express the divergence and curl of this in terms of the scalar potential, vector potentials. We obtain last step is made with the help of the operator form BSC rule that the term this vanishes. Yeah. When did this come from? Oh yeah, this is just from this, but without this because it vanished. Um, in this way, we can see that divergence of V is related to scalar potential, while curl of V is related to the vector potential. It's possible to make these relations quite explicit, although we are not in a position to derive. It's possible to make these relations quite explicit, not in a position to derive final results until section 4. We begin by point. Well, you're going to do it anyways. We will not do it, but we will do it. We begin by pointing out that this this messy thing that I have made messy, this uh, has the form of a poison fish equation. Mm, the Laplace is it correct to say the Laplace? The del squared of the Laplace squared of the gradient of this scalar potential, is that it? We begin by going out that the double squared of the scalar potential equal minus S of R. What is S? Well, they're going to tell me. Where S is the divergence of V. Well, this is a nothing burger because this is just this. We just carry the negative across. What is the point? Where the charge density of electrostatics is now denoted S of R. Charge density, like point, has the form of a Poisson. I'll say Poisson because maybe mathematicians are French. We begin by pointing out that as a form of Poisson, blah blah. Oh, so this is just a form of a Poisson, I guess, where the charge density of electrostatic is now denoted this. The scalar source dense, where the charge density thing of electrostatics is now denoted as R, S of R. The scalar source density of phi. Scalar source density of phi. Scalar is now denoted as this. So they're kind of equivalent, you could say. Charge density, scalar source density. I guess it just means the same thing. Charge, scalar source. Scalar source charge. From electrostatics, we know that the electrostatic potential due to a charge distribution is blah blah ah, R12 R1 S of R charge density density charge density, so Q over M cubed. This the tau here is just volume, so M cubed. Yeah, this is just distance M charge per meter, scalar source density of. We know that the electrostatic potential. I forget the units for electrostatic potential. Ah. I'm trying to remember any equations from that. E equal potential. I'm sure if I had one equation, I could get everything I needed. Hence, the scalar potential can be written explicitly as this, this, d tau 2, R12. So they're just saying SR is the divergence of V. What are we even doing? It is possible to make these relations quite explicit, although we are not in a position to derive the final results until this. We begin by pointing out that this has a form of a Poisson equation, where charge density is now denoted as S, blah blah. From electrostatics, we know that this is equal to this. Hence, the scalar potential up here, can be written as this. So we reason that this, since this is of the form here, we can like substitute it into here, and then switch around subject of formulas to be like, oh, we can be like this is this up here. Ooh. Hence, the scalar potential can be rewritten as this. Okay, similarly, 1.110, we deal with the curl now, shows that each component AI of R, shows that each component AI of R of the vector, shows that each component AI of R of the vector potential, also satisfies the Poisson equation. Hence AR has the explicit solution. How is this the Poisson? Oh yeah, I can see. Uh, mm, oh, I was gonna say it's not a Poisson because this, let me change colors. Because this guy is a scalar and this is a vector, but they explicitly said each component is like a Poisson equation. So you just split this into three. So this is three scalars. And then you can do Poisson shenanigans, where SR is the curl. SR is a curl. Um, and then over here you just switch this guy up here with the curl. Yeah. I am making sense. So AR is this. I kind of don't like that they're grouping up all three. Like, they're putting all three of them into here. I would have much preferred if it was like AR equal 1 over 4 pi, big bracket, integral, curl of phi I. Well, summation of I 1 to 3. Hmm. Hmm. Yeah. I was just gonna do plus, but I realized I can do a summation thing. Big bracket, summation, I, how do I do this? 1 to 3. I forget. Um, 1 to 3, I equal 1 to 3. I 1 dot 3. Um, of the integral of the curl of phi I over R1 2 d tau 2. Okay, I would have much preferred this, but let me see if I can reason out just from this how this could be this. Hmm. Okay, I think I see it, but this isn't helping at all. So this cross V1 plus this cross V2 plus this cross V3 over R12, R12, R12. You can just change this into one big fraction where all of them is over R12. And this cross V ends up being IJK del LX, del Y, del LZ, VI, VJ, VK equal del VK del Y minus del VJ. This is not a del VJ del X. I did not sign up for this. Del C, del Z, del Y VK, del L, del L Z V J. We got 6 terms. Okay, maybe I don't know what I'm doing. This turns into 6 terms. This turns into 6 terms. Uh, hmm. But like at the same time, this turns into 6. This turns into 6. Does it? What is this cross VI? VI. Uh, wait, what do you want AI? What am I talking about? AI, not VI. All the 3 AIs combined make VR. I think. Wait, this is not anything to do with AI. Hence, the scalar, blah blah blah. Okay, let's go back. Similarly, this shows that AIR of the vector potential. So we have this equal minus SR, where this is SR. Satisfy, hence AR has the explicit solution. AR equal bling. Yeah, these are all V's. AI has nothing to do with this. AI is just in one side of the equation. V is on the other side. We're only dealing with V's right now. Okay, back to this. V, well, what is V? V is a vector field, right? So a vector field is at every point there's an arrow. There's a different arrow. Maybe it don't have to be different. It just needs to be like an arrow. This cross VI. This cross VI. VR2 specifically means 1 point, and it has 3 components. Does it? Yeah. The 3 components is just the I, the unit vectors, basically, multiplied by the magnitude, of course. Okay, so VI is just a unit vector, which means IJK, this cross thing here, gives us del LX, del Y, del LZ. And this will just be something. Maybe it's just, let me make sense of this. VI, it'll just be the magnitude of V, I guess. And this will be 0, 0. So the I component will be 0, 0I, minus this, del V del Z, Oh, minus minus, so it's plus j plus k del y del v del y k. Okay. Um. Okay. So this has 6 terms, and each one of these gives us 2 terms. So yeah, it checks out. 2, 2, 2, 6. Let me try to zoom in a bit. Del vk del y del vk del vi del vi. No, this is j. I think this is a weird j. Um. hmm. I think this is this, but this is negative though. This is negative. So maybe I'm mixing it up. What are we doing? Del del y del vk del y del del vj del vj. I mean, I'm sure if I compute all these results and compare to these results, it'll be the same. So in other words, I am fine with this. This is good. Is there anyone in chat? Nobody's in chat. We move. Okay. Um, thus the divergence on curl of a vector field, the divergence on vorticity of a vector field can be interpreted as the source density of its scalar and vector field. Source density of a scalar vector field. Source density. What does that source density even mean? Source density. Source density. Deploying density means how much of this is packed into the sum of the space. Source. The divergence and curl of a vector field can be interpreted as the how much of this thing is in this thing in this space of its scale can be interpreted as the density of its scalar and vector potential. So the scalar is the source and the vector is the source, is how I'm reading this. Once the structure of a vector field is understood, it is easy to form a physical picture of a vector field used in physics. Structure, physical picture. Let us consider Maxwell's equations in vacuum in SI units. Um, We see by inspection that these equations summarize the following experimental facts concerning the two vector fields E and B of electromagnetism. The source of the electroscalar potential, source of the electroscalar potential, the scalar potential of the electric field is proportional to the charge density. The source of the electrovector potential is Faraday's induction. The source of the electroscalar potential, source of the electrovector potential electroscalar, electrovector. Boom, boom. There's no magneto. There's no magneto scalar potential because the magnetic monopole density is found experimentally to vanish everywhere. No magnetic because the magnetic monopole density is found experimentally to vanish everywhere. The magnetic vector potential, oh, it is just equal to zero. I see. Um, that is the vector potential A originates from ion actual current density. Um, or Maxwell's displacement current density. Okay, because given inspection. Okay. In other words, Maxwell's equation described the physical nature of the four source densities. Four source densities of the electromagnetic field. So we have two vector fields here. And we saw that we can break them up into curls and divergences of we can describe them fully from the curl of it and the divergence of it. And what does the source have to do with this again? Can be interpreted as the source density of its scalar vector potential. And what is the scalar vector potential? Ah, ah. The fields this and this are called the scalar vector potential. Boom, 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 boom. Source density of its scalar vector potential. In other words, Maxwell, blah, blah, blah. Equation 1.15. Equations are known as Maxwell's equations in honor of this stuff. This discovered in 65 with displacement current. In the absence of this displacement current term, the fourth equation gives a result of equals 0. Without a displacement current, you see that 0 is equal to a constant times the divergence of J. That violates charge conservation as expressed by the continuity equation, this, which says that the divergence thing plus this equals 0. Like the change in charge density, the charge has to go somewhere. Um, so it's just like earlier. I think all the pattern I'm picking up is all continuity equations have to do with like a decrease in something. So when the charge density decreases, the change in the density over time is the negative of it. Ah. Um, it gives the result this that violates the conservation of the violates charge conservation when the charge density changes in time. The missing term del P del T when expressed in terms of the electric field with the help of Coulomb's law, gives rise to Maxwell's displacement current. Okay. I saw a really good physics video on this a while ago. So I kinda grasped this decently well. Like if I rewatch that video, I'd be really good. Good job. Um, Problems. I don't have a problem. Okay. We're at the we're at orthogonal curvilinear and coordinate systems. I think this one is gonna be I think once you understand this, you're in a good place. So that's why I think I like this. But we'll take a break right now, I guess. Anybody in chat? Tensorial analysis. I'm not there yet. I don't think I'm close. Maybe, maybe I am. The chapters quickly. Hmm. This textbook goes into Fourier stuff. I don't know how closely that's related. Um, you're probably gone by now. Um, Let me get all this sorted. This is just this is the second chapter of this book. It goes into root square spaces and stuff, which I don't know what that is yet, but we'll see. Um, I don't know. I think tensors are just an upgraded form of vectors. You combine vectors in a certain way. That's my understanding of it. Um, yeah. Yep, yep, yep. I'll drink water. Alright, let's get back in the sauce. How long have I been serving? A little under an hour. Okay. Blah blah blah. Okay. In discussing vectors and fields in space, we have so far used only the rectangular or Cartesian coordinate system. It's intuitive since it makes use of straight lines, perpendicular directions, the simplicity of the differentiating and integrating makes us really fond of them. However, physical systems are not naturally rectangular. Yeah, we see from spheres and stuff, from charges. The inverse square law. Um, the inverse square law really likes spheres. Um, a sphere is a good example. Rectangular coordinates. The rectangular coordinates of a point on its surface are changing from point to point. A sphere is a good example. Rectangular coordinates of a point on its surface are changing from point to point. What does that mean? But in spherical coordinates, the spherical surface is specified simply as a surface of constant blah blah blah. The choice of coordinate systems can be important in description of physical systems. A good choice could be simpler maths and more insight into the description of the properties of said stuff. There is a price to pay. There is a price to pay for this improvement. Coordinate systems other than rectangular, far less intuitive, harder to visualize. The integration, differentiation is a little more complicated, harder to memorize. Just the following sections show. I don't know what tractable means. Maybe it means doable. It's quite tractable, perhaps even enjoyable when approached from a certain point of view. This turns out to be just a matter of changing directions and changing scales, as we shall see. Okay. Let us begin by noting that any three independent variables, U1, U2, U3, can be used to form a coordinate system if they specify uniquely the position of a point in space. I'm fine with that, yeah. It's convenient to start with the rectangular coordinates x, y, z equal x, blah, blah, blah. To start with the familiar x, y, z and specify the new generalized coordinates in terms of these. ui equal ui x, y, z. For the transformations between these two coordinate systems to be well-defined and unique, it is necessary that the inverse relations also exist. Well-defined and unique, and that all these relations are single-valued functions. For example, the spherical coordinates may be defined in terms of the rectangular from these equations, or from these, and you can switch back and forth. There's two ways. A coordinate axis now becomes a coordinate curve along which on the coordinate axis now becomes a coordinate curve along which only of only one of only I think they're missing a word here. Only one of the coordinates is changing. So normally if you're going, I get what they mean earlier in one of the sentences they were saying earlier. To go from here to here, you would need to change the x, y, and z, or maybe just x and y, depending on plane shenanigans. But for spherical, the r remains the same. All you're changing is the theta. So yeah, the coordinate axis along which the coordinate curves in spherical dynates. Let me Google what dynates mean. Dynate meaning. No, dynate. What? Dynate meaning maths. I still don't know. I'll find out from context clues, I guess. Uh, okay. The coordinate curves in spherical denotes dynates. I don't know what the coordinate curves in spherical dynates are radii for variable r. I really don't know what this word means. The coordinate curves in blur are blur. Longitudes for variable colatitude angle this, and latitudes for variable longitude angle this. Okay, I think from context clues, dynates mean Spherical. What? I think I know what it means, but now the grammar doesn't make sense. The corner curves in spherical dynamics system, like that, I mean system. Okay. It's easy to find algebraic expressions describing these coordinate curves, because by definition only one of the coordinates changes along such a curve. So coordinate curve is one where um, only one of the coordinate changes. I see. Hmm, maybe I should write that down. Um, the color is white. Uh, tool window color. Color, not white. Anything but white. Chord curve means, well, only one, I'll put UI, because that's what they were trying to get at here. Only one thing is changing. Changing? Wait. Hmm. Because I'll explain why I paused. Because in my head I was thinking, oh, this is just an equipotential line. But, hmm, but for equipotential line, only one thing is constant, right? Hmm. Maybe it's like a curve, like an area. Oh, I'll understand better the more I read. Only one thing is changing. Um, okay. Oh, look, this guy is still there. It's an error in the book. Spherical coordinates are radial. Diagonal coordinate. Okay. Thank you, my good sir, my friend. Oh yeah. I don't know how I didn't pick that up. It's just the end of they just missed out chord. The coordinate curves in spherical coordinates are radii, variable r, longitudes. It makes much more sense. I don't know how I didn't see that. Thank you. Um, it is easy by definition only one of the coordinate changes along such a curve, while all the others remain unchanged. For example, r equal RER in spherical coordinates. Example, this equal this in spherical coordinates. Then the partial derivatives describe the vectorial changes along these curves. Yeah, that makes sense. Each of these derivatives is a vector in space. Blah, blah, blah. Yeah. It has a length hi and a direction ei. I equal r. Hmm. I'm curious, how much math do you know? Like, what's your level? Okay. Each of these derivatives is a vector space. Yeah. Has a length hi and a direction ei. I equal this, or this. There. So instead of I being 1, 2, 3, or XYZ is R theta phi, um, the explicit forms can be obtained readily with the help of rectangular coordinates. Hmm. del r of r is this del theta r. Del phi r. Do they have any diagrams? They do not have any diagrams. Ah, okay. Okay. I'll draw my sickle. Sickle. Um, R equal R ER. Magnitude, direction, radial direction. Del R R. Let me look at these. Del R equal del. The explicit forms can be obtained readily with the help of your rectangular coordinates. Del R equal del X EX. It's Y plus CEC. I agree that R is this, yeah. So to get from here to here, del R. Del. I assume this goes to this, this goes to this, this goes to this. So let me try and section it off. Well, maybe it doesn't. Del R X sine theta cos phi. I'm not circle brained enough. Oh my god. Hmm. This is like for context. I read, like I skimmed this book a little bit, like earlier. Well, not the entire book, only the first few chapters. I skimmed it. And back then I was able to digest this much easier. Like this part here. But I guess it's kind of harder now. Like maybe back then I was more, like, I had studied like spherical coordinates better. Hmm. Maybe I should just read, and then maybe it'll come back to me. Okay. Um, Simple calculation then yields HR equal 1 ER H theta equal R H theta H phi equal R sine theta. What simple calculation? Oh no. You can factor the R here. You can factor the R to get cos theta cos phi, cos theta sine phi, minus sine theta equal H bling. They're saying H bling H theta equal R. So all this stuff should be 1, right? Surely. Hmm. Did I miss a page? Because I remember them. Wait. I remember this was more fleshed out. Like UI to XYZ. We move. 58, 57. Yeah. I did not miss a page. Okay. R sine theta. Oh yeah. So me factoring out this thing actually is what they actually are doing here. Because you can get R sine theta from here, you can get R sine theta from here. Sine phi plus cos phi. Um, Sine phi cos. But you also need to include these guys. Sine phi ex plus cos phi ey. Hmm. Hmm. Oh, and all of this is just with R. Is R. Hmm. Okay, no, never mind, never mind. Okay, and therefore dr, a change in R. Okay, like this for a portion of my yap just now. In my head, I thought this R meant the radius, but this R just means the position vector from the origin to the place in the sphere. Not yellow, purple, nice sphere. Okay, so we have R here. That's a really straight line. We have R. Okay, well, let's say R goes from here to here. So this is a change in R, dr. Del R. I feel like I might have to make a lot of little triangles. Like if I really want to go deep into this. Okay. Are you still here? Let me check. There's no chat, so I assume you're not here. But that is okay. Okay. Yeah. But at least this is cleared up to me now. Like this is not radius, this is R, position vector R. And therefore the change in the position vector equals um hmm, 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 R d dr equal. I'm trying to think in like um in normal Cartesian. Hmm. Del del in school they didn't really touch on partials that much. They just told us how to do partials. They didn't really say dr equal del. Hmm. I feel like if I had this for the Cartesian coordinates XYZ, I'll be in a better place right now. Del R, del X. I feel del R, del X, where R is a position vector again, plus del R, del C, del Y, plus del R, del C. I feel like this is the situation, yeah. I feel like this is a thing that is true. Could be wrong. And in spherical coordinates, they're doing the exact same thing, where, um, wait, but these guys have dr and d theta and d phi. Hmm. Hmm. Oh yeah. It makes sense. I forget. I forgot. You really need these drs and not dr, dx, dy, dc. Because I think at the end of the day, the partials about the The partials are about the change in like a particular direction. So this del x means the change in the x direction. Um, but you still need to multiply that. You still need to connect it to the actual change. I don't know if I'm making sense. Okay. Ah. Okay. So I agree with this so far. Yeah. And we found that del R del I don't want to call this R anymore. Del position vector. There's a mouthful, but I prefer to say that. Del position vector del R. Or maybe I just say radius. Del R del radius. I feel like that's better. Del R del radius. But it's not really the radius. Maybe I can say del radial. It's all just semantics. Is that the word? It's all just words, anyways. It doesn't matter. Um, del position vector del R dr. Del position vector R dr del R is equal to this. We found out from here. Good. We found out del position vector del theta equal to hmm, yeah, equal to this. H theta E theta. Yeah. So there's nothing fishy going on yet. Nothing fishy. Equal dr. Okay, they found the length of HR to be 1. So 1 H theta equal R. Yeah. H theta blah blah blah. Yeah, good. Okay. And it's important to note that hmm, hmm, del x dx del x x y z x y z. Okay, let's move with this for now. For arbitrarily generalized coordinates, UI, U2. Okay, they're getting back into this. This is where everything becomes clear, hopefully. For arbitrarily generalized coordinates, U1, U2, U3, coordinate curves. Coordinate curves can be determined in a similar way by examining the displacement dr and dr equal del position vector. Oh, I can say r again. Del r del u1 du1 del r del u2 du2 del yeah, correct. I agree. Each partial derivative by examining the displacement. Each partial derivative. Oh no, there's a different sentence. Yeah, I never noticed, but they put full stops. Yeah. Each partial derivative equal del x del ui ex. Hmm. So all this is just from one guy. So del r del ui equal del x del ui ex. That's del y. Blah, blah, blah. Hmm. Each partial derivative is a vector. Each partial derivative is a vector. Is that the case up here too? Yeah, it is. With a length and a direction. That also makes sense. Um, mm, they have the tangent vector in brackets. Each partial derivative is a vector, the tangent vector, del x del the tangent vector. So this has me thinking of just like the basic like idea of differentiation. Well, not the idea of it, but the result of differentiating. Like if you differentiate a function, you'll get the gradient at that point. Um, well, gradient throughout the function. So that has me thinking like this is a nothing bigger. This isn't saying anything because we know the differentiation is just a tangent. Um, each partial derivative is a vector, the tangent vector, with a length and a direction. Okay, well, there's no summation here, which is something to note. Um, hmm. Yeah, there's no summation. So HI is actually three guys in one. The direction of HI, well, not HI, but yeah, I guess HI, you can call it HI. The direction of HI combines all these guys. Hmm. Okay. Where HI equal, well, yeah, this is how you get the length of something in coordinate geometry. Pythagoras, yada yada, yata, I don't know. Yeah, I agree with this. Um, yeah, it makes sense now. Like this part makes sense. Um, I was wondering where these sine thetas and stuff went, but when you square them, you'll get all kinds of sine squared and cos squared, and we know that sine squared plus cos squared equal 1. So when you have squared sines and coses, they tend to disappear. So it makes sense why these results are simple. So good. So for future reference in this book, if I don't fully understand something, maybe it will be made clear by stuff later on, is what I gather from this. Um, okay. I'm liking this. I'm understanding. In terms of these quantities, the original displacement may be written in the form dr equal the summation of I, dr equal the sum of these guys. Um, basically, hmm, okay. Initially, we broke up dr into the changes in the change in each like axis. Yeah, axis. Initially, we broke it up into the change in three axes, and then each one of those is a vector. So we just simplified it by calling it hi, and hi has its magnitude and direction. And to get this back, we're just adding up the hi's. Yeah, makes sense. Hi, ei, dui. What is this dui about? The hi, ei is just hmm, HIEI, that's just the H vector. DUI, DUI. HI equals del R del UI, which is this, which is this. Okay, it makes sense because we still have to multiply it by DUI, which which is what they have here. So yeah, I agree. And summation AI. So they pulled out EI, and they're saying that H of R um, DUI is equal to DSI. Okay. Thus, EIR defines a coordinate curve. Coordinate curve, only one thing is changing. Two things constant, one thing changing. So let me break this down for myself. Two things constant, one thing changing. X constant, so X is constant on this, wrong, wrong. Uh, X is constant on this line, where this is the X axis. Y is constant on this line. What is the Y axis? This is the axis. And Z could change, but so the only way Z could change and not affect these guys is in the normal to here, like at that specific point. Is that a correct thing to say? Is it? C, X, Y, Z. I feel like it is. So the coordinate curve of, like, in Cartesian coordinates, the coordinate curve where one thing is changing and two things are changing is literally just the tangent of, wait, okay. And this by itself, you can make this into its own coordinate system. X is not changing, Y is not changing, Z is changing. So like this, what I'm thinking now is that there's, depending on where X and Y is, you can have like infinite amount of coordinate curves that satisfy the restrictions that a coordinate curve is. Um, okay. Yep, yep, yep. Okay, let's go back. Thus, EIR defines a coordinate curve. In terms of these quantities, the original thus EIR defines a coordinate curve. Okay. So let's try to compute one term, one expression from it. One term, I think, one term. So EZ, uh, EZ, HIDUI, HC, DUC. Okay. Thus EIR defines a coordinate curve. EIR. This is just a position unit vector. Does this change? EIR defines the coordinate curve. Well, H2 is, well, HI still deals with like partials, and there's, okay, I don't know, this is just in magnitude. Okay, will all will be made clear at some point. Thus, this defines a corner curve. I could accept that for now, since it gives the unit vector tangent to the curve at R. Yeah. All I need to do is just finish the sentence, and I will be in a better place when I just stop midway. That's both a good thing and a bad thing. Like, I'm figuring it out for myself, activating the neurons. So it's like what I was saying up here, where it's like all of this is all about one point, and you can have like every in different point we have a different curve. That's just what I get from this. Thus, EI defines a corner curve, since it gives the unit vector tangent to the curve at R. The infinitesimal scalar displacement, that's a new thing they're defining here. Infinitesimal scalar displacement gives the displacement along this corner curve. Okay, yeah, I agree. HI is just a length after all. HI dui. The function HI of R is called a scale factor since it ensures that the displacement has the dimension of a length. Since it ensures that the displacement has the dimension of a length, irrespective of the nature and dimension of the generalized coordinate UI itself. It ensures that this. Okay. Okay. The function does ensures that displacement. Mm, nature and dimension of the generalized coordinate UI. DUI. DUI. Okay, so what I'm getting from this is that, wait, does that even make sense? What I was gonna say is, they're saying HR is called a scale factor, and it ensures that the unit ends up as meters as a length. So I was thinking maybe this, maybe UI, change in UI. Hmm. I was thinking maybe change in UI could be something other than length, like, like it could be force or something, but it could be like the electric field or something, like the electric potential, but I don't know. We will see. I'm not throwing away this idea though, because it still kind of makes sense. Maybe we move. Uh, other geometrical quantities. When, okay, I'm getting close to, well, I already passed an hour and a half. I don't want to go on for too long. It's good that I'm understanding, at least. Okay. Um, other geometrical quantities can be calculated readily. Other geometrical quantities can be calculated readily in terms of these scale factors and the unit tangent vectors. Okay, they're just talking about EI and HI. Thus, the infinitesimal scalar displacement ds along a path in space is, oh my god. Okay, this is giving off tensor vibes. I could be wrong. I could be wrong though. Thus, the infinitesimal scalar displacement ds along a path in space, let me just draw a path, is this thus is throwing me off. What do you mean thus? Like you ought to have something preceding this. Other geometrical quantities. And maybe they're talking about tensors, I don't know. Other stuff can be calculated readily with the HIEI system. Thus, the infinitesimal scalar displacement ds along a path in space. Scalar displacement. Okay. ds. At the end of the day, ds is just hi dui. So ds is just a length. Yeah. You're not really doing anything. Okay. The infinitesimal scalar displacement ds along a path in space is blah dr dot dr. Where g equal where g this saying gr, so this is multiple stuff, are called the metric coefficients. This saying r because there's a summation there, so there's multiple terms there. Where these are called the metric coefficients of the generalized coordinate system. Metric coefficients of the generalized coordinate system. Metric coefficients. So what I'm getting from this is when you change a coordinate system into like the HI, EI, like this kind of, when you figure out the HI, EI stuff for coordinate system, you are generalizing it. Maybe, yeah, maybe. And there are coefficients are called the metric coefficients of this. Metric coefficients of this. For some reason, you need coefficients. Okay. Blah 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 blah. GRJ. Wait. Maybe this R is for this because they're saying where this R, not this R. So maybe this is multiple stuff for real. Okay. Let's just continue. The differential elements of surface and volume can be written down. Oh yeah. The geometrical quantities they're talking about, yeah, is the area, differential area and differential volume and stuff. Is differential volume a thing? It probably is. Maths gets really like insane the more you delve into it. The differential elements of surface and volume can be written down with the help of 1.26. That's so far up. With the help of 1.26. With the help of baby stuff. Okay. I might need to scroll up to get that. Okay. The differential um, area element equal the cross of hmm, what is this? Del R, del UI, DUI. Del R, del UI, DUI. That's this. Okay, and it's just two guys. 12 Cowboys, Ravage. Um, DR, the differential area element, IJ. The IJ is just saying like there's multiple like areas you can do like X, Y, X. We saw del X, del Y, del C. Well, it's just saying which ones are crossing basically. So the result of this should be in the direction perpendicular to this plane, whatever. Okay. We've established that this is HI. This would be HJ. So that's how we have this here. This is just the constants though. With all the directions. The directions remained cross multiplied. And the UI and the UJ are treated as constants as well, it seems. I I can get behind that, yeah. Yeah. Um so nothing happened here. And they're saying HIDUI. Yeah, this is just the S, yeah. They're bringing Tau back into this. I don't like when they bring Tau back, but I guess Tau just makes it clean, right? Where you can factor out stuff. But every time a Tau appears, I have to do a bunch of stuff with fractions and then cross it out and be like, oh, this is this for real. Blah blah blah. Okay, and the Tau. Oh no, they're just talking about differential area element now. Equal ds1, ds2, ds3, and then there's like ABC, like I forget what they call this. But this can be expressed as a determinant, and there there's something called a Jacobian, I think, and that is also a determinant. So that's what this is here. The differential volume element, which I assume that's what this is. Yeah, that's what they're talking about. Equal ds1, ds2, ds3. Um, and then you just combine these guys. Yeah. So apparently, I'm assuming J means Jacobian, right? So apparently Jacobian means the, I forget what you call this. I feel like this is the volume of a parallel. I'm not even gonna attempt saying it. Parallelepiped. Like a 3D parallelogram. I don't know. It's something like this, right? The Jacobian is just a determinant made up of the unit vectors. That's what this is saying. J equal dx dy dz dy du2 du3. Hmm. Never mind, never mind. It also includes this. Wait, what? Hmm. The units make sense, right? Because you want to return back to dx dy dz. H1, H2, H3. H1, H2, H3. Oh yeah, ds just breaks down into H. Hmm? Oh, what is ds again? Hi dui. Hi dui. Hi dui. Yes, yeah. The h's end up inside there. Jacobian equal h1, h2, h3, and then this. Okay. It's called, yeah, J is called a Jacobian. It is the 3D generalization of J equal dx du in the 1D change of variable. It is a 3D generalization of in change of variable dx. Change of variable. Okay, dx equals. So let's say you want to change the variable from dx to du. You do that by finding out the relationship, basically dx du, and then to make sure you end up with dx, you have to have another du. Uh, okay. And then you call the thing in front here j apparently. So you can be like, oh, look, I changed the variable by just adding this number, but it's not actually a number. It's um, it is a variable change. It's a differential. It is something. It's not a number, but j makes it look simple. So you can do j. You can do this stuff in one dimension, but the Jacobian is like 3D. We can do it in 3 dimensions. Wow. I'll end stream like very shortly. Um, I just want to see if I find out anything. Like I want to write the determinant for this and see if I find out anything. So E. Wait, what? E1, right? E1. E1. Have I ever done a determinant outside of XYZ? Outside of a Cartesian? Does it work differently? That is a question. Let's assume it works the same, um, regardless of coordinate system. So E1 would just be uh 1 1 0 0. Is is that a sensible thing? EI E1 just means 1 0 0. That's it seems like this will lead nowhere, but okay, I'm just more confused now. 0 0 1. And when you do this determinant, you'll find out that 1 times 1 equal 1. Well then, uh, my headphones was falling out of my head. Okay, doing this has made me more confused. D tau area the volume element will ds1, ds2, ds3, and then you have this left over. H1, H2, H3. H1, H2, H3. Hmm. Hmm. Maybe the point it's trying to make is that, like, all this. No, no, no. Hmm. Hmm. Football, yeah. dr to dr equal gij dui dy. Gij. Is this? I need to erase. Is it a J or I? Is it J? Okay. dui duj dr dot dr. X component. X component of this. X component of this. We saw that we can break up dr into this, right? So the X component, the not X component, the one component, the one component. What is the one component here? Because maybe there's components in here that is also one. Hmm. But or I think all of these has ones in them. Hmm. Which would explain why this is complicated. Because if this is tree one guys, and this is tree one guys, it'll get complicated, yeah. Okay. Um, hmm. But I think I'll stop streaming now. These streams are getting like consistently longer. Like my first one is 90 minutes, the next one is like 90 plus 10. Now this is like 90 plus 20. Goodbye, if anyone is here. If this guy is still here. My first chatter, yes, ooh, spooky. Um, and they helped. You helped for like a little bit. Goodbye. The end. The end. Bye.